And then after that, we're going to take the panel debate. So Wouter, please.
Yeah, thanks.
The stage is yours.
Thank you very much. Right. Well, as mentioned, my name is Wouter van der Velden. I work at Dassault System. Just in one sentence, let me say it like this. I mean, Dassault Systems is an engineering software company, right? So we are producing, developing engineering software solutions, and that goes through the entire life cycle. I have a short, I would say, marketing or more marine and oriented video for us from our side to highlight and show what we are actually doing.
From food to trade and energy, vast and powerful seas have always been essential to our world's prosperity. But if we are to realize the full potential of the ocean economy, we need to rethink a more responsible and sustainable path. We need better, safer, greener assets. From smarter ships designed with high-performance hulls, new materials, and alternative propulsion systems, to offshore assets capable of harnessing new energy and natural resources. It is time to transform the marine and offshore industry, innovating new business models and processes, leveraging advanced simulation, analytics, smart automated manufacturing, standardization and modularity, bringing operational excellence throughout an asset's entire life cycle with digital continuity, by enhancing the real world with the virtual world. Dassault System's 3DEXPERIENCE platform unleashes a new wave of innovation, empowering the next generation workforce with deep knowledge. From ideation and engineering to manufacturing and asset in operation, the entire value network is connected into a single collaborative environment, unlocking the true value of our oceans by harmonizing product, nature, and life. In a future made possible by virtual universes, experience the future today.
I know I think you saw quite an amount of buzzwords already coming in. Apologies for that. But it tackled a little bit open platform, to the experience platform, which I will talk about a little bit more, but also, of course, simulations, right? And those are the kind of the three main pillars I would like to work on. So what we've seen is a major transformation, right, of the marine industry. It's triggered by new regulations, new technologies, especially with the net zero emissions by 2015. There's an acceleration going on, right, in innovation, which we also learn from other industries. Think also about new propulsion, new materials, and any other, I would say, advancements in technologies, which you can see there on the right-hand side. So this means that ships become more automated up to the level of autonomous ships or maybe even drones, right? And this transformation is happening, as you all know, in a complex environment. There's limited scales, there's reduced workforce currently also, budget restrictions, of course, and also all kind of other stances which we have to take into account. So to overcome this, what we are kind of proposing, right, is that we should go beyond the digitalization. We want to integrate knowledge and know-how, and we're going to do that with virtual twins. And I know there we have seen a lot of words about digital twins, and my presentation today more is on virtual twins. And what we are trying to offer with virtual twins is the unique opportunity to accelerate the transformation of the marine industry, right? We reuse knowledge, we simplify the increasing complexity of systems, and we allow to become model-based, right, instead of document-based, which we used to do. So this creates a context of intelligent data to reply, for example, on artificial intelligence, and also to allow to automate the engineering of ships, but also the processes of entire shipyards eventually. So for the marine industry, virtual twins basically are available for ships with the integration of MBSE. We've already heard a lot about that. ModSim, which is actually kind of the abbreviation of modeling and simulation. Generative AI, modularization. Modularization is a very important topic as well, but also the integration, of course, of real data or real ship data into the virtual twin, so conditioning monitoring. And the shipyard, on the other hand, right, it's kind of directly consuming this data for optimized and automated production, which allows us to make offering predictable time, cost, and quality, of course. So it's not just the smart ships or the ship which benefit of that, also the shipyard itself, right, and the way we build up the shipyard. So by implementing virtual twins, we're kind of overcoming 3 major challenges. The first one we're looking at is basically the readiness for future ships. So that's about innovation, simulation, energy efficiency. Second one, workforce challenges. It's about robotization, automation, new technologies like AR, AI. Third one is improved profitability and capacity. So we've optimized planning, supply chain, predictability and visibility, for example, of project execution. So while this virtual twin technology implementation, we are basically moving the industry from a traditional document-based engineering to a model-based engineering. Basically, this is relying on those 6 blocks. You see on the left-hand side, again, the 3 categories I just mentioned. So the first one is model-based system engineering, so allowing to define, for example, cyber physical systems. The second one is ModSim, modeling, which is basically extending the systems to multi-physics simulations. Third one, model-based approval. So basically, the sophistication of future ships would require you to increase the regulation compliance. We have model-based manufacturing, which is related to consume basically the model you create in the production operation. And we have model-based collaboration because, of course, and we've talked about it before, efficient project execution is crucial and often also requires, therefore, a single source of truth, which would make life easy. And then finally, last but not least, is model-based sustainment, which is there to reduce time and cost of maintenance and maximizing then ship capacity. So today we kind of focus on the top 2, MBSE and modeling and simulation, also simply because we're today here at the Open Simulation Platform Conference. I think this is the third time you're going to see the V diagram. There's already been in 2 other presentations. So on the left-hand side, define and decompose requirements, right? On the bottom, we have implementation. And on the right-hand side, we see the integrate, verify, and validate, which is basically needed, right, to build up our system requirements. The color-coded arrows in between indicate kind of the risk or the rising risk of realizing basically a mismatch later, right, in the V cycle. So obviously, if you're far in the end, you see a red arrow because that's, yeah, problematic. So how can we mitigate that? And this is actually very important, and that's why we're also all here. We want to include simulation. We want to introduce simulation earlier in the design process. So for example, even after just defining the requirements, we would like to check if those requirements are quickly met with the help of simulation. And that can be either lower fidelity or higher fidelity. So simulation, you can see, can help us to reduce risk because you see the color coding of the arrows changing, right? Actually, we can make life easier. We can introduce more simulation, maybe an ideal scenario, but I'll come back later to that. We see risk are even reduced further. Also, the quality of risk matter, of course. What if at an early stage you can already cross-check your simulation with, for example, higher fidelity types of physics simulations, so multi-physics type simulations, co-simulations, for example, right? And this is where we see the importance. At Dassault, we have quite a large tool set to cover that. I'm not going very significantly into detail, but what I want to focus on is that we all have these solutions on one single platform, which is the 3DEXPERIENCE platform. We can integrate the power of MBSE with Rectify, CATIA Magic, Daimler, as well as ModSim with Somalia. So I'd like to explore this a little bit better. I've taken one demo, which is a real-time interactive co-simulation engineering demonstration, which is featuring basically a submarine drone. So as you can see on the screen, the goal is basically here to integrate simulation results from external sources, such as experimental data or field test data, and we're going to feed that directly into the system model within the V-cycle process. So this model then, at the end, would be able to communicate through an FMU protocol to control the submarine drone simulator in real time. So a lot of overlap with previous presentations, as you saw. So all of this is centered around that virtual twin, right? This is the most important thing which I like to highlight. So this acts as the digital backbone of the entire MBSE cycle, which helps us to continuously correcting or connecting the requirements, design, validation, and simulation. In a nutshell, this is the entire, I would say, workflow or process. You start at number 1, right, where we have tools like Rectify to manage stakeholders' needs and standards. It basically can automatically capture document structure, lets you tag and identify requirements. So very helpful if you have the documents from the classification agency which you would like to import. And it also organizes it then directly into your overall project specification. Next, step 2 and 3, related to CATIA Magic. This system is basically building a SysML architecture. This captured the stakeholder needs, mission definition, system context, operational and functional scenarios, but also the conceptual architecture of the drone. Then you see in step 4 the 3D model being created, adding, for example, also mechanical and kinematic details. And then in step 5 and 6, we move over to basically system simulation engineering. So this is done with Daimler based on Modelica, where we develop dynamic system models. These can be derived then from the 3D design directly and automatically, right? Which ensures basically continuity through the process. And these models then can represent the submarine, its control system, environment, and scenario, and so on. And after the simplification, it's then also exported as an FMU to simulate the behavior and drive a so-called, in 3D site, so creative experiments situation where we can run a virtual, a VR, as you can see, for example, in step 9. So I have a short video of this, a very short video, because I had to reduce this quite a lot. But this is kind of a great example, right, of MBSE in action, where we have stakeholder needs and standards move over to the preparation phase, the operational analysis, the system architecture as well, and then basically creates the virtual twin by developing a 3-dimensional model. That's something you see here, right? We can check the kinematics of the model after it's been built. And then that model is automatically being exported to what you can see on the right-hand side, right, into a 3D model. And then that drives basically the system simulation model. And then finally, in this case for VR applications, right, the system can then be transferred, for example, in a real-life gaming simulator, as you can see here. You can connect your Xbox controller to your Windows system, and you can actually play around with that, for example. So at Dassault System, we believe in expanding the use of advanced simulations, and that's actually originally also my background, multi-physics simulations. But of course also code simulation techniques, right, in the system development side. However, introducing these methods can raise challenges, of course, for the need for a specific subject matter expert, right, which we need to be addressed or needs to be accessible. So let's explore how we like to resolve this. So on the screen you see, it's an aircraft model. Apologies for that, but you can see a system model showing an aircraft, its subsystems, 3 requirements basically. It's a very simple model: maximum weight, maximum stall speed, and minimum range, right? Well, since the system engineer is not an expert in aerodynamics, for example, he will call, email, or meet with a subject matter expert and say, hey, I'm evaluating these requirements against this system, right? Can you tell me if these requirements are feasible or not? So what we have to do, right? The subject matter expert will turn into phone calls, emails, meetings with other teammates and say, hey, I have aerodynamic fluid simulations. Does Bob have, for example, the weight calculations from the CAD model? Or does Sue have the range evaluation spreadsheet from Excel? So they all run all of those simulations together, although still separate, right, to check those numbers. Ultimately, they will be able to communicate, of course, back to the system engineer and say, hey, with these numbers you gave us, you meet or you don't meet those requirements. And I think everyone can imagine here, right? The human in the loop process here is slow, inefficient, non-scalable. It introduces additional risk of human errors. It also lacks of rigorous traceability. And it also lacks of the opportunity to perform meaningful trade studies, because we can do this, of course, thousands of times, right, without a large hit to personal availability. So what we're proposing basically is to support this by the means of our 3DEXPERIENCE platform. So what we can do is subject matter experts can develop and publish model templates, for example, of their higher fidelity simulations, and share them in the platform with the system engineers. So these templates could also be onboarding some of the system engineers' low fidelity applications actually, or replace them to make it more accurate. And this can obviously also can be done through different kind of communication protocols. So the system engineer can then integrate those templates directly in the system model to verify requirements, leading to a decreased reliance on human-in-the-loop processes and enabling better traceability and scalability. So the net benefit, what you see here, is provided that the system engineer itself has found a way to increase his system analysis frequency with high accuracy, and therefore reducing, of course, risk later in the design cycle. That's exactly what I just explained before with the V cycle. So how does this type of templating work? I have a short demonstration here. How are they? How open are they? How do they connect with other tools? So first of all, an SME, so subject matter expert, will develop and validate their models. Just like they do today. This can be virtual twins on our platform. This can be 1D models, as you can see, but it can also be in-house tools or external applications. Then secondly, the engineer, the subject matter engineer, will compose a simulation process to define the workflow and connect all this necessary data. This open format allows the use of various adapters to enable to connect everything from virtual twins to in-house tools, etc. And then thirdly, they publish it as a template. And then after that, you can use this template in your SysML model, right? So the system engineer can use this in his architecture model, and it will be able to, for example, launch a Cameo orchestrated simulation using the model the expert created before. So we've seen how this helps, right? We've seen how MBSE helps. We've seen how basically left shifting, because this is what we're actually doing, right? We're left shifting simulation earlier in the design cycle helps. So ModSim helps. I want to kind of conclude with the openness, right? Because it's of course also a topic of today. And the platform which we've been worked on already for decades, right? It's of course, I have to say it's flexible and open, but I want to show you a few details about that. It's not just only about app integration, as you can see on the top-hand side with third-party apps. It's also, of course, a connectivity with the enterprise ecosystem. You need to link with PLM, ERP, MES systems to support end-to-end workflows. But also the flexibility extends outwards, right? Which is important. We've seen this before. We have to communicate. OEMs, suppliers, and partners have to collaborate. And if they collaborate on the same virtual twin, of course, precisely managing data sharing and maintaining a unified source of truth, we see all kinds of benefits coming in. So what's truly flexible and openness? This kind of relies on these four pillars. Of course, you can plug in data from multiple sources in a wide range of formats, thanks to file converters. Core capabilities can also be extended through APIs, letting you customize and integrate with unique workflows. Seamless automation is possible thanks to the templating and process automation. And then you can also extend the model itself, tailoring to its specific business requirements needs. So I have very quickly those four pillars before I end my presentation. Very obvious. Here you do break, of course, the chain, I have to say, but you can, of course, always start with converting data, right? So the system can support importing and exporting a wide range of third-party formats. I'm not going into any of those details on the right-hand side, but you can see a list of import or export function depending on the arrows. The list consists of multiple CAD formats, but also typical system engineering formats and engineering solutions are included. So that will be, of course, your first step. But I think more importantly, when import and export may actually interrupt this, the single source of truth, right? Adapters and connectors are essential for ensuring then the openness and flexibility. So you can use these, and standard connectors for many third-party applications are out of the box available. And in addition, also this type of API is open. We have an open API there which allows third-party developers to build their own connectors to work on the platform with our virtual twins. And this allows them then for a smooth and disruptive-free transition. With automatic and on-demand generation of neutral formats, we also add another level of flexibility. This is part of our connector portfolio, supports widely used industry standards. I'd like to say a few brief words about the logo you see there, also the OCX format. So this is a very important format which is now being adopted by the marine and offshore industry, right? So this is something also with our partner, iTech. They've been developing basically an OCX to 3DEXPERIENCE convergent tool that preserves then the data quality. Because the future is basically relying on this OCX format, because we see that, for example, digital 3D classification processes will going to improve collaboration among, of course, different classification societies, but also the designers, the builders, and the owners, right? And this accelerates the approval It also would replace eventually the 2D drawings with the actual 3D models. And then we can focus on that next step, which we all hear about, is then connected to our simulation solutions, right? So for example, evaluate the structural integrity of your hull. This is a topic I already explained. So we talked about this process composer capability. We can connect this, of course, with our in-house tools. I haven't said anything about that today, but the Dassault system portfolio has solutions related to fluids, so hydrodynamics, aerodynamics, electromagnetics, acoustics, structures, and motion. But obviously, it can also communicate through our own code simulation services or through any open standard like FMI or also MPCCI. And then depending on the setup, we can use more simple algorithms or maybe also more advanced algorithms, something we have in-house. Another final point there to mention is if you connect externally, you see there on the bottom right side, the node OS command. That is a very powerful adapter. Looks a little bit silly, OS command, but what does it mean? It just allows you to connect to your OS and execute whatever you would like to do or whatever you like to use. And in that way, you can bring it into your virtual twin, your processes, and connect the data, input and output against it. Finally, if it comes to enterprise integration, this is again something which we work on with open APIs. We can connect to a various set amount of enterprise integration solutions to basically connect to various other PLM systems, ERP or MES systems, so manufacturing systems, allowing this single source of truth to keep there, right? So summarizing basically on the openness, we provide this unified environment. It brings together model and data-driven applications. It's tailored for all kinds of different industries, as you can see from the top, from design to simulation to manufacturing to operations. And as you can see on the list, there's quite a large set of industry standards or connectors, which we do offer within our solution portfolio. And this list, of course, is continuously growing or also actively maintained to ensure that you guys have the compatibility you would like, right, with the latest protocols and technologies. To recap, what I like to say today is that we are shifting from this document-based model to a model-based shipbuilding, which would accelerate design cycles, reduce risk, also improve, of course, the collaboration. A model-based approach provides the digital continuity across disciplines. It will help you to better system architecture and manage that, and also to complete the traceability, right, in an environment where you all have to share data. And then with MBSE and simulation, we can bring multi-physics and co-simulations much more earlier into the design. Think about the V-cycle I show. This allows us to do faster validation and smarter trade-offs using standardized engineering methods you might have in-house, right? And then finally, basically the backbone of all of this is the 3DEXPERIENCE platform, which ties together then everything which is offering the openness, automation, and integration of basically a complete enterprise system, which enables us a connected, efficient data model for digital shipbuilding. And that's it. Thank you very much.
Thank you, Wouter.
I hope it's a good start to the next session.
Well, I couldn't see how it would be a bad start for the next session. Questions? And yeah, there was one in the back there.
I have a question. Could you estimate how computationally demanding could this twin be?
I think there are various aspects in terms of the computational demanding of a virtual twin, because I think first of all, you can build a virtual twin with your own laptop if you have a GPU card, right? However, as I mentioned before, the virtual twin is more than just a static object. We like to say that the virtual twin is tying, like, let's say, all the aspects together, right? So I think the more demanding part probably would be to build up the model itself, right? Which moves probably human resources to some extent. Much maybe more than the computational power, because I think the computational power would more be in in the type of simulations you select, right, and choose to integrate in your model. So, and this is the trend which we all see in terms of surrogate modeling, which I think was discussed before, language models, et cetera, is that we see the shift of still the need of doing, for example, higher fidelity physics. We need those because it can help us driving, for example, models in the future, right, or approximation models in the future. So I think it's a very, probably I'm not really answering your question now thinking about it, but it's a difficult scenario to address, but I'm not necessarily looking into the disadvantages of computational power or whatsoever, no. But just to understand, is your question related to if you really the software solution or the architecture, or just more in general the building the virtual twin? I see. So it's really purely on the software part. Yeah. No, you don't need a data center, right? I mean, and again, the levels of virtual twins can differ, but especially for a ship and a shipyard, you do need a huge amount of data. And that's either handled indeed on your own systems or on the cloud, which if I have to pitch, it's something we offer as well. But yeah, that's any software solution is offering that. So yeah.
Any more questions or comments?
Yeah.
Yes, he will. So maybe we can segue into this year's panel discussion.